Last lecture. It's been fun. Hope you've enjoyed it. We're going to finish up missing data today, and then for an introduction to Monday's lecture by Ray Carroll, I'm going to talk about study types a little bit. So observational studies versus experiments, randomized trials, that kind of thing, because he's going to talk about clinical trials. So last time, we started talking in more detail about multiple imputation as a solution for missing data, and mentioned that that rests on a Bayesian foundation. So we reviewed Bayesian ideas. A posterior distribution is a probability distribution for a parameter. We treat a parameter as being a random variable in Bayesian analysis. So we're interested in the probability of theta, a parameter, given my data. Typically in frequentist statistics, we talk about the probability of data given a parameter value, a likelihood. The posterior distribution, according to Bayes' theorem, is proportional to a prior distribution, so that's a probability distribution that we specify on the parameter itself, proportional to a prior times the likelihood. Likelihood requires that we know a distribution for the data. Prior requires that we have some kind of knowledge or are willing to make some assumptions about where the parameters are likely to be prior to seeing any data. We talked about what are called Jeffreys priors. These are non-informative prior distributions for parameters generally, but in particular, since we're talking about means and covariances, there's a standard non-informative prior for a mean, a standard non-informative prior for a variance or a covariance. These, in the context of what we're considering, posterior distributions that we're going to deal with, specifically with multiple imputation, are these two. So a posterior for a mean, or a mean vector, being multivariate normal, and a posterior for a covariance matrix being inverse Wishart. Okay, so multiple imputation has, it's an iterative algorithm, and it has two pieces to it, or two steps. The first is called the I step. The I step is where we actually impute the data, so missing values. We do this by drawing from a distribution for the missing data, conditional on the observed data, and our current estimate of the parameter vector. So by drawing from a distribution, we not only fill in the missing data with an expected value, but we also have randomness associated with it. So if we're doing regression to impute these missing values, we could say y miss equals beta 0 plus beta 1, in our case, times diagnosis score. So if you tell me what diagnosis score is, which I know for everybody, I can predict what pain is based on that regression model. That would give me a constant fixed fitted value for each missing pain observation. What stochastic regression would do is take that fitted value and add a random error term. So we talked about that in the context of the HERS data, where we regressed one of our covariates, glucose, that had missing data on the other covariates and the response. So we got a regression model for my missing variable in terms of the other variables for which we have complete data. That would give me a fitted value for SBP with 130 and non-smoker who's white, non-diabetic, a fitted value from that regression model of 95.45. But that's not exactly what I plug in for the imputed value. I plug that in plus a realization from this normal distribution, mean 0 with this residual standard deviation. So I'm adding in random error to account for the uncertainty involved in filling in a missing data point. Otherwise, I have the same problems that we talked about with single imputation. So I fill in the data in the I step, And then in the P step, I create new versions of the parameters, the parameter estimates. So when I plug in the data in the I step, I now have complete data, and it's straightforward to estimate the parameter values. So once I have complete data, the mean vector is just the mean. The covariance matrix is just the sample covariance. So that gives me a mu hat and a sigma hat. What I do next is I use that mu hat and that sigma hat to generate randomly a new mu hat and a new sigma hat from the posterior distributions for each of those parameters. So I say that capital sigma becomes a random draw from this posterior distribution for capital sigma, conditional on my current estimate of mu and my data. So that means I draw from this inverse Wishart distribution that we talked about as the posterior for a covariance matrix. Similarly, I draw from the posterior distribution for mu, given the current estimate for capital sigma and the data. That comes from the multivariate normal distribution like we talked about a moment ago. In more general contexts, multiple imputation, I impute the data in the I step, so that looks like this. A general distribution for the missing data given the observed data and the current value of the parameter vector. Generate from that to plug in missing values. And then generally generate a new vector of parameter values theta from the posterior distribution for theta. When I'm just dealing with a mean and a covariance, these are separate steps. I have a covariance posterior, I have a mean posterior. But generally, if I have a bunch of parameters, I'm doing a regression model, I want a posterior distribution for all those parameters. So here's the pain example and how we can do multiple imputation with these data. I need starting values for the parameter estimates. I need a mu 0 hat and a sigma 0 hat. And what we're going to do is take the MLE estimates as our starting values. So we computed these using the EM algorithm previously as the MLEs for these parameters. The initial I step, we're going to say, in the pain example, what we're doing is treating just two variables. We're treating the pain variable and the diagnosis variable. And we're talking about fitting a regression model for pain in terms of diagnosis. Pain has missing values, so I want to impute pain and then fit the regression model. Once I have these parameter estimates, we talked last time about how I can use them to estimate the corresponding regression coefficient and the residual variability. So specifically, if I know the covariance estimate between the diagnosis and pain variables, and I know the variance estimate for the diagnosis variable, then beta 1 hat is just equal to their ratio. Beta 0 hat is my estimated mean for the pain variable minus beta 1 hat times the estimated mean for the diagnosis variable. So that gives me my regression model. I also need this residual variability. With these MLE estimates, that corresponds to these coefficients. So beta 0 hat equals minus 0.057, beta 1 hat is 0.123, and then sigma hat squared p given d is 5.32. Given those, I can do the I step again. So I essentially now have a regression model for my missing variable in terms of the observed variable. I can use that regression model to fill in or to impute with fitted values plus residual variability. Once I have these quantities estimated, my missing pain observations equal beta 0 hat plus beta 1 hat times the corresponding diagnosis observations plus residual variability. So a draw from the normal distribution mean 0 with that variance. That gives me imputed data, a complete data set. with the complete data set, I can recompute my estimates, mu1 hat, sigma1 hat. So this mu1 hat and sigma1 hat correspond to doing one I step. So randomly, these were randomly obtained. If you did this in your code, you'd get slightly different answers, but this is from randomly drawing from a normal distribution with that variance, mean 0, gave me data on the basis of which I could estimate with these resulting numbers. That's the I step. The P step is to take these estimated parameters and my data and generate randomly from their posterior distributions new versions of sigma1 and mu1, the matrix and the vector. So when I did that from the inverse y-chart and the multivariate normal, I got these two quantities, the covariance matrix sigma1 star, the mean vector mu1 star. So you would get, again, different values. These are quite a bit different in some cases. So the estimated variance for the diagnosis variable went from, in the MLE case, 189.6 to, after imputation, 199.58. And then when I randomly generated from the inverse y-chart, I got almost 500. So variances vary quite a bit, can vary quite a bit. The variance for the pain variable didn't change as much, and the variances for, or the imputed versions of the means changed a little bit. But I generate new random versions of my parameter estimates, and then I repeat. So once I have mu hat and sigma hat, I can do the imputation. Once I've done the imputation, I can estimate these parameters again. Once I've estimated these parameters, I can generate random versions of them from their posteriors, and then I repeat. The second round, my I step gave me these regression coefficient and variance estimates. Those gave rise to these new, gave rise to new mu and sigma estimates, and then these were randomly generated from the posterior distribution. So I step, P step, and we do that many, many times. We do that until what's called convergence. But convergence in the context of multiple imputation is not convergence like it is with the EM algorithm. The EM algorithm is trying to maximize the likelihood for the parameter in terms of the parameter values. So we converge if the estimated parameter values don't change much at all between iterations. That's how we gauge convergence. With multiple imputation, we're not getting increasingly better estimates of the parameters. We're just getting new estimates, randomly generated, of the parameters. So convergence has to do with achieving what you could call like a steady state of the random generation procedure. So here's what that could look like. Here's a couple of diagnostic plots for gauging convergence in the context of multiple imputation. So it refers to the distributions of the parameters becoming stable and no longer changing in a systematic fashion. So if I start from bad initial values, the estimated parameters are likely going to change quite a bit early on. Eventually, they're going to achieve a steady state that looks like something like this. This is when we call the posterior distributions stationary. So they're not changing in a systematic way. This is one diagnostic plot that's used for gauging. So you do a bunch of multiple imputation rounds, maybe 1,000. You do a whole bunch of them. And then you look at a picture like this to gauge which of these imputed data sets should I pull out for my imputed data sets. The reason I look at a picture like this is because the coefficient vectors, the coefficient or parameter vector at one iteration is correlated with the parameter vector at a previous iteration. Because these are randomly generated from starting values that are the previous parameter estimate, subsequent parameter vector estimates are going to be correlated with their preceding ones. In terms of generating new completed data sets, imputed data sets, I don't want correlation between the new data sets. I want randomly generated new data. So what I look at in a picture like this is how many iterations should I put in between those for which I'm going to draw out my imputed data. So I might look at a picture like this. This is a time series plot of the mean for the pain variable. I can look at this and gauge, or try to gauge, correlation. So there's correlation apparent when this plot changes in a systematic way like this. So for increasing pain estimates, I tend to continue having increasing pain measurements. For decreasing, I tend to have decreasing continuously pain estimates. So I see what looks like correlation between the imputed data sets in this range. Here's another systematic peak. Here's another systematic trend. Some systematic trends here. So what I might look for in a picture like this is what's like the lag that I should impose for drawing out random versions of the data. Versions of the data that have escaped this correlation pattern. So for example, I might say 100 iterations. After 100 iterations, I would claim, based on this picture, there's correlation, there's some correlation, correlation, correlation. It looks like it has returned to the same basic area as the initial pain measurement. So I'm going to say that after 100 iterations, I'm confident that I have broken the correlation between this data set, this imputed data set, and this imputed data set. So I might assume that there's correlation between data sets within the first and the 100th iteration. So I look at a picture like this to gauge or to decide on what lag should I use in picking out imputed data sets to use for my final analysis. I might do 1,000 imputations, a whole bunch of them, look at a picture like this and pull out 5 or 10. Another diagnostic plot is an autocorrelation plot where we have lag on the horizontal axis and we have a measure of correlation on the y-axis, vertical axis. So for estimated pain means that differ by, let's say, 5 iterations. So the first p-step compared to the 6th p-step, and the second p-step compared to the 7th p-step, and so on. You put all those pairs together that differ by a lag of 5, and you compute a correlation between the corresponding pain means. And in that case, we got a correlation of 0.45 or so. So what I might do with a picture like this is look for what lag do I require in order to make the correlation sufficiently small. Sufficiently small is subjective, just like this picture is subjective, but you do the best you can. So you look for this correlation to get small, and it will level off at a really small number. So in this example, I might say 100. 100 might be more than I need. A lag of 100 might be more than I need. This autocorrelation plot seems to suggest that 35, probably 50 is sufficient, but I've done a bunch of iterations already. Why not just take 100 to be safe? Okay, so when I do that, actually I'm going to take every 200. I don't remember why I chose that, but to be extra safe, I guess. 100 is probably fine. Once I've made that decision, I have, say, 1,000 imputed data sets. I'm going to take every 200th one. So I'm going to have 5 imputed data sets that I'm going to use in my final analysis. 5 complete data sets. Simulation evidence suggests that 5 or 10 is sufficient for achieving high efficiency relative to the maximum likelihood estimates. So you do very well with multiple imputation with just a handful of imputed data sets. You only get the highest efficiency, though, in theory, with an infinite number of imputations. So the more imputations you have time for, the better your results are going to be. The lower the imputation standard errors are going to be. Software by default will typically give you between 5 and 10 or 5 and 20 imputations. Once I have 5 or 10 imputed data sets, I have 5 or 10 completed versions of my data where the pain variable has no missing values anymore. What do I do now? Now I estimate the model of interest on each of those imputed data sets. So in our case, we're interested in the regression model of pain in terms of diagnosis. For each of my 5 or 10, for each of my 5 in this example imputed data sets, I would fit this regression model. That would give me estimates beta 0 hat, beta 1 hat, and standard errors for beta 0 hat, beta 1 hat. For each of my 5 imputed data sets, I would keep track of those coefficient estimates and those standard errors. What I would like to do eventually is combine those coefficient estimates and those standard errors into a single coefficient estimate and a single standard error. So if I want to do inference on beta 1, say, it's not clear what to do if I have 5 beta 1 hats and 5 standard errors estimates. I could do 5 confidence intervals and make a subjective interpretation of those. What I would like to do is be able to have a single confidence interval or a single p-value for beta 1. Here's how I do it. I have 5 beta 0 hats, 5 beta 1 hats, and I have 5 standard errors for each one of those. I want a single estimate, I want a single standard error. At the end of the analysis phase, where we have capital K, in our case 5 sets of model coefficients and standard errors, I create a single estimate of one of my parameters, so beta 1, say, beta 1 hat. I would say beta 1 tilde is just equal to the mean of the 5 beta 1 hats from the imputed data sets. So 1 over capital K, sum up the parameter estimates from the imputed data. So that's easy. I just average up my parameter estimates from the imputed data. For the standard error estimates, it's a little more complicated. You don't just average up the standard errors. You have to account for 2 sources of variability. So to combine the standard errors, we compute 2 different quantities, what's called the within imputation variance and the between imputation variance. The within imputation variance is what you might expect that you get to do, but you don't get to do. This is just the average of the standard errors, or the average of the squared standard errors. V underscore W, the within imputation variance, is just the average of the squared standard errors. You also need this between imputation variance, VB, which is a sample variance of the parameter estimates. So theta hat T minus theta tilde is my single estimate. So I average up, or I sum up the square deviations of my capital K imputation-based parameter estimates from their overall mean, divide by one less than the number of imputations. So it's a sample variance of my capital K imputation-based parameter estimates. If beta 1 hat was what I was talking about, this would be beta 1 hat T minus beta 1 tilde. The total sampling variance, which is the basis for the overall standard error I'm going to use for my overall theta hat, or theta tilde, beta tilde, is V total, which is V within plus V between plus V between divided by K. So it's a correction factor out there on the end. There's basically a sum of the within and the between variances plus a correction factor, which, as the number of imputation goes up, goes to 0. So for lots of imputations, the overall variance for my imputation-based estimate is just the sum of these 2 variances. But in general, I have to have this correction factor. So let's see what this looks like in practice with the pain data. Here are the data. down at the bottom is the multiple imputation code. I need a couple of packages. I bet I don't have this one. MC pack and mass. Mass comes with R, but I bet MC pack is not there, so let me install it. MC pack is the package that I'm going to use for an inverse Y-sharp distribution. That's not a standard distribution. It's a Bayesian-based distribution. Where did my, okay, here we go. Going to try a different mirror. Oh. How do I force quit an application on Windows? You know? Start task manager. RGUI. Comes now. Program is not responding, and now Windows is checking for a solution to the problem. There it goes. Okay. Let me open up R again, see if I can make this work. So we need MC pack. Let's use a different mirror. There we go. Okay, and then down to my multiple imputation code. All right. So I'm going to actually do a whole bunch of imputation iterations, 5,000 of them. Don't have to do that many, but I'm going to do it because it doesn't take that long. So capital B is 5,000. Theta 0, mu 0, and capital sigma 0 are the maximum likelihood-based estimates. So I need to rerun my EM algorithm to get those. And then my initial values for mu hat and capital sigma hat are those corresponding estimates. So theta 0 was the vector containing all the parameter estimates. The first two elements were the means. The second element, or the third element, was the variance for the diagnosis variable. The fourth element was the covariance, and the fifth element was the variance for the pain variable. So I'm making a covariance matrix by pulling out each of those pieces. Pulling out the bits of the data that I want to work with, and then initializing some empty pieces to hold on to things. Capital B not found. Okay, so here's my loop over capital B iterations. The I step is here. And so what I'm going to do is I'm going to use my initial estimates of mu hat and capital sigma hat to estimate the regression model for pain as a function of diagnosis. beta 1 hat, beta 0 hat, sigma hat, P given D, using the formulas from the notes. Once I have those, I can impute the missing pane observations. So YP1, the updated complete version of my data. All I have to do is fill in where there are missing values. Beta 0 hat plus beta 1 hat times the diagnosis variable, that's the fitted value, and then I have to add in a random draw from the normal distribution with mean 0 and standard deviation, the square root of my, or standard deviation, the residual standard deviation from my regression model. That gives me the current version of the imputed data. With the imputed data, I can recompute or re-estimate mu and capital sigma by just using usual MLE formulas. So mu1, updated mu hat, is just the mean of the two variables, diagnosis and pain, now with the complete version of pain. Capital sigma 1, the new version of capital sigma hat, is just the sample variance of those two variables. So now that I have complete data, those are easy to compute. The P step is to randomly generate new versions of my parameter estimates. So capital sigma 0, the updated, what will be the starting value for capital sigma in the next iteration, is from the random inverse Wishart distribution, n minus 1 degrees of freedom, capital sigma 1 times n minus 1. So what I need for the second parameter of the inverse Wishart is this capital lambda hat, where capital lambda hat, did I define it? Yeah, capital lambda hat is the sample sum of squares and the cross products matrix. So that's all that is the covariance matrix without the scale, without n minus 1 in the denominator. So that's what I have here, capital sigma 1 times that scale. Randomly generate a new mean vector from the multivariate normal distribution using the updated estimate of capital sigma. That's for the next iteration. So now I'm going to keep track of let's see, where's my standard errors? Oh, we're going to get that later. So that's my loop for doing multiple imputations. So let's run that. That's going to give me capital B imputed data sets, a whole bunch of them. I made the holder, the variable that's going to contain all of the 5,000 imputed data sets, I made that be a list. So length of data impute 0 is 5,000. The first element of this list is a complete version of my data. So my diagnosis variable and my imputed pain variable. So these are now imputed values, randomly drawn error terms plus fitted values from the estimated regression model with pain as a function of diagnosis. Gauging convergence, I'm going to look at diagnostic plots for each of my parameter estimates. Here's the parameter, or here's the time series plot for the diagnosis mean variable. Here I'm not actually doing any imputing. The diagnosis variable had no missing values. So this should just be random draws from the posterior distribution for this variable, which would indicate that there is no correlation. There's no correlation between subsequent draws because I'm not imputing the data, so that the previous iteration's data doesn't have anything to do with the current iteration's data. It's always the same. No correlation. So I don't need any lag with respect to this variable. I will for the other variables that have to do with pain. Here is the pain mean, the plot corresponding to pain mean, and I see clear correlation chunks for this variable. Between 0 and 50, there's a pretty systematic spike. Between 50 and 100, there's a systematic trend. 100 and 150, So I might choose, I don't know, you might choose 50 because it looks like every 50 it has returned to the same neighborhood. I chose 200 because I have plenty of bootstrap or multiple imputation iterations. Here's the corresponding picture for the diagnosis variance. Here again, I don't expect there to be any correlation because there was no missing data. So this looks like as random as you're going to get. The covariance estimate should have some correlation because it involves the pain variable. And then the pain variance estimate. Not so much, but there's a big spike in between 0 and 50. So I'm going to choose 200 based on that picture. Can also look at autocorrelation plots. Here's the autocorrelation for the diagnosis mean. Shouldn't be any correlation. Sure enough, it drops down to basically 0 at the first iteration. There is no correlation, regardless of lag. For the pain mean, there is correlation, substantial. Looks like after 50 or so, it's pretty small. 200, it should be tiny. And so on. So here's the variance for the diagnosis variable, no correlation. Variance or covariance variable, some correlation, and then the variance for the pain variable with correlation. All right. So I have decided that I'm going to use every 200th iteration to pull out imputed data sets, capital K imputed data sets from my 5,000. K is equal to 20. Is that right? 200 times. I guess I'm just going to pull out 20. I'm going to pull out 20. I'm not going to use all 5,000. So I'm going to pull out 20 from every 200th imputed data set. Once I have those, then I fit my model for each of them. So capital K, 20 imputed data sets. For each one of them, loop over 1 to K, I'm going to do my model, which we said was just a regression model for pain as a function of diagnosis. So this is a completed data set, the ith completed data set, second column, that's the pain variable, tilde 1 plus first column, which is the diagnosis variable. I'm pulling out the coefficient table, which has the estimates and the standard errors. I'm only going to keep track of beta 1. That's the coefficient I really care about, the relationship between pain and diagnosis. So I'm going to pull out the second row, and then I want the estimate and the standard error. I want to keep track of both of those. So the first and second columns of that coefficient table. That gives me 20 pairs of beta 1 hat and standard error of beta 1 hat. What I do with those is I pool them by to construct a single estimate of beta 1 and a single standard error for beta 1 hat. I do that by averaging up the beta 1 hats and by computing these two quantities, the within and the between variance. Within is just the mean of the squared standard errors. Between is the sample variance of the beta 1 hats. And then I put them together as the square root of the sum of the within and between plus that correction factor, b divided by capital K. So my final estimate of beta 1 is 0.118. My final standard error for beta 1 hat is 0.08. So using that, I can do a test, I can do a confidence interval. That's multiple imputation. There are a couple of packages that do multiple imputation. MI, I think, is the most widely used. It's kind of finicky. So in this case, when I run the code, it breaks. It does not, in my case, it does not converge. So they have some fancy diagnostics for deciding what lag you need in order to achieve no correlation between those lags. And with these data, we'll see if it works here, but with these data, for me, when I ran it a few times, it did not converge. Let's see, I don't think we have the MI package. Let's get it. Don't have the mice package either. I need both of them. So the MI functionality requires that you initialize your missing data. So you use this mi.info function, and then you use the core MI function to get multiply imputed data sets. So that gives me capital K imputed data sets. I think it gives me 5 by default. And then there's a function, there's a variety of functions for fitting a model using the imputed data sets and then doing the pooling that's required. For linear regression, there is a built-in lm.mi function that when I specify a formula, will take the multiply imputed data set or variable from mi and do the regression, get the capital K estimates and standard errors, and then pool them like we need to. Here's the estimated result. We've had this problem before. And I don't know what the solution is. So I installed MI, and then it tells me there's no package called MI. So I'll leave it to you. It works for me on my computer. Maybe it's a version issue. That's code for using MI. Again, when I use it, I don't get convergence. There's another, it's an older package, or actually this one might be the newer one, called mice, that does similar things. I use the main function mice to get imputed data sets, and then I apply the lm function. I can do that with the with function, and there's a pool function for taking the collection of lm outputs and getting the pooled estimates and standard errors. So here's what I get, and in this case, they don't match well what I got when I did it manually. So I think the multiple imputation code is finicky. It's going to vary from implementation to implementation necessarily because there's randomness involved in the imputation process. The estimated beta 1 that we had, beta 1 hat, was 0.117. The estimated beta 1 for mice was 0.08. I trust 0.118 because I got that out of a textbook. I matched something from a textbook. I don't know why mice is not matching that well. My estimated standard error, beta 1 hat, was 0.08. The estimated standard error from mice was 0.05. So technically doing multiple imputation, but I'm a little wary of it. Okay, so that's missing data. Remember that it's an important consideration, but it's one that gets short shrift often. We typically just let R throw away our missing data and do pairwise deletion, not worrying about it. But there's a lot of cases where with missing data, you can think up a reasonable scenario or explanation for the missing data being missing at random. And when we have missing at random data, there can be substantial biases in the results of our estimates and inference if I don't account for the missing data correctly. So that's that story. And then on to, for a moment or two, some notes on study types. Got 5 minutes. So again, Monday's going to be clinical trials. That's an example of a experiment. An experiment. There's different types of there's different ways that we collect data, and there are different qualities associated with those different ways. There's some approaches to collecting data that give us better information, in particular about causation, than others. So there are observational studies, there are experiments, various flavors of observational studies, case reports, which is where you have a doctor who observes a patient and sees interesting things and writes it down. I have one patient for which when I give them gummy bears, their cancer went away, say. Cross-sectional survey, case control studies, and cohort studies. I'll show a little bit more detail about those in a second. Experiments, the gold standard is a randomized controlled trial where you randomly assign a simple random sample of individuals to different comparison groups. So that allows you to get unbiased estimates of effects for a drug, say, where you can control for confounders, confounding variables. The fact that you randomize into two different groups or multiple groups means that there shouldn't be any systematic difference between the populations that wind up in those comparison groups. So you shouldn't get all males and all males in the treatment group, all females in the other group, and any other variables that might be confounders that you don't even know about. By randomizing to the different groups, you break any systematic issues there. So that's the main thing about randomized controlled trials. You eliminate, at least in theory, and on average, confounding. That's why with experiments you can talk about causation, but not with observational studies. So there's a hierarchy of evidence that's suggested observational studies give you information, but it's limited information because in particular you can't get rid of the possibility of confounding because of the nature of observational studies. Experiments are better. Meta-analysis of experiments is even better. Meta-analysis is where you take a collection of experiments, say, and you pool all the information to get even better information. Case reports, these are observational studies or observational data. This is one individual. So a doctor has one patient that shows interesting symptoms and response to a treatment, say. It's anecdotal in nature. There's problems with publication bias where if I see something interesting in an individual, I can publish that, but if I observe an individual and there's nothing interesting, I don't publish that. So there's potential for we only see things that look interesting in publications. A cross-sectional study is a standard observational study where you just observe, you enroll a sample from a population, and it's only at a specific time. So this is not longitudinal data. It's certainly not an experiment. For example, I might enroll a bunch of people from the United States, a bunch of adults, and ask them about their alcohol consumption and assess their disease status, cirrhosis of the liver, for example. So I have data on consumption of alcohol and cirrhosis of the liver. I could do a regression model of like a logistic regression model of cirrhosis, yes or no, as a function of alcohol. And I could get a coefficient estimate. Here's the estimated association between alcohol and cirrhosis, but it is an association. It's not necessarily an effect of alcohol consumption. Because this is cross-sectional, it's observational, so that cirrhosis, the perceived relationship between alcohol and cirrhosis could be driven by confounding variables. There could be other variables in the background like diet or whatever, genetics, that really are driving cirrhosis. Alcohol is just there as something that's related to that variable, so confounding. There can be individual or aggregate level cross-sectional data. Aggregate level could look like data on nations or data on census tracts or counties, that kind of thing. The problem with aggregate data is there's this potential for ecological fallacy. For example, rich states tend to vote Democrat, but rich individuals tend to vote Republican. So if you just look at the state level, you seem to think that rich people would vote Democrat. But there's a paradox that even though at that aggregate level you have one picture, at the individual level you can have a totally different picture. So there's big limitations of cross-sectional studies. Case control studies, this is, we're out of time, but this is where you enroll people based on their disease status. So I'm going to enroll you based on whether you have cirrhosis or you don't. And then I'm going to look back and ask you about your exposure. How much did you drink in the past? Smoking and lung cancer is a big example of using case control studies. Instead of enrolling people and observing their smoking and waiting 25 years for whether they get lung cancer, I enroll people based on whether they have lung cancer or don't, and then I ask them about their smoking status. So it's kind of a backwards assessment, but it does give you information about associations. So we'll quit there. You can look through these if you want to. Cohort studies, experiments. So cohort studies, there can be prospective and retrospective cohorts. That's longitudinal in nature. And then randomized controlled trials are the gold standard for assessing causation. And that's what Ray Carroll will be talking about on Monday, clinical trials. All right, any questions?